Ang pag-aralan natin sa presentation na ito, ang steam and geothermal power plant. Ang fuel na diesel, sa nakaraan nating topiko sa diesel power plant, uh, atin itong ihalo sa air at ilagay natin sa loob ng cylinder. Sa loob ng cylinder, atin itong susunugin. Nang ating ito sinunog, magkaroon ito ng pagtaas ng pressure na siyang tutulak sa piston. Nang itulak natin ang piston, mag-generate ng work ang ating cylinder. Yun ang konsepto ng conversion ng ating energy mula sa thermal energy ng diesel fuel papunta sa ating work ng diesel engine. Samantala, kapag ang ating fuel naman ay hindi liquid fuel, like say coal, a solid fuel, mahirap po ito ilagay sa loob ng cylinder para sunugin. Kaya, gumawa tayo ng ibang mga paraan upang ma-utilize natin ang energy mula sa mga solid fuel, kagaya na lamang ng steam power plant. Sa power plant, meron tayong container. Ilagay natin doon ng tubig, and then susunugin natin ang ating solid fuel, say coal, at ang heat doon ay ating ilagay sa ating boiler. So mag-vaporize ang ating water sa loob ng boiler at high pressure P2. Dahil mataas ang pressure na iyan, ay sapat na iyan upang paikutin ang ating turbine. So nag-expand doon sa turbine, and then ang ating turbine ay nag-generate ng work sub T or work ng turbine, and then ang condensate at ang vapor ay ipinunta natin sa ating condenser, kung saan atin naman itong i-condense. Kapag i-condense natin, ibig sabihin hihigupin natin ang heat mula sa loob ng condenser. And then, i-pump natin pabalik ang ating water doon sa ating boiler. Kapag ito ay gumagana according to Carnot cycle, ito ang magiging hitsura nito sa ating TS diagram. Meron tayong dalawang working pressure, higher pressure side and the lower pressure side. And then, kapag isabihin natin ang state ng water before entering the pump is state 1, sa Carnot cycle natin, it is somewhere here sa TS diagram. And then, after exiting the pump, lalabas ito as a saturated liquid at point 2. So sa TS diagram, it is a saturated liquid. So tinansya natin na ang ating point 1 is such that after delivering the water to higher pressure, its state is saturated liquid. From point 2 naman, dinagdagan natin ito ng heat at nag-vaporize ang ating tubig from saturated liquid to saturated vapor at point 3. So at point 3, the state is now saturated vapor. From point 3, in-expand natin ito sa ating turbine. And the turbine generates work, and the state of the water after exiting the turbine is state 4. Ito po iyon. And then, from point 4 na naman, i-condense natin up to point 1. At point 1, ang state ng water natin is a mixture of liquid and vapor. Majority is condensate, pero meron pang mga vapor. Okay. Pagtitingnan natin, bakit hindi natin ginagamit ang Carnot cycle sa actual na mga power plant natin? Let's say, sa actual na mga steam power plant natin. Okay. Isa sa mga dahilan nito ay ang point 1. Kung saan, mula sa point 1 papunta sa point 2, kailangan natin i-pump or i-compress ang mixture of liquid and vapor. Mahirap po gagawin yun. Mahirap i-compress or i-pump ang liquid and vapor ng sabay. Kaya wala tayong practical or wala tayong steam power plant na gumagana in Carnot cycle. Ang total heat na inilagay natin dito sa ating Carnot cycle or sa ating plant is equivalent to this red area. Samantala, ang heat naman na nireject natin is equal to that blue area. The net area there is the net work done by the plant or the net energy available in the plant. Okay, mag-consider tayo dito ng halimbawa, meron tayong Carnot cycle. Ito yung mga proseso natin. Una, ang tanong dito is, ano ang thermal efficiency? Okay, alam natin ang thermal efficiency ng Carnot cycle is 1 minus TL over TH. Meron tayong higher temperature, 250, at ang lower temperature naman natin is the temperature of the condenser, which is 60.06 degree Celsius. Given this value, ma-determine natin ang efficiency ng ating cycle, which is 36.3%. Okay. Next is the amount of heat rejected and the net work output. But before that, unahin muna natin ang net work output. Dahil meron tayong efficiency at meron tayong meron tayong heat added. Ang heat na added natin is the heat added from saturated liquid to saturated vapor. That is HF and HG. The difference of which is HFG. So, ibig sabihin, ang heat added natin is, that is the Q in. Ang value nito ay ang HFG natin, 1715.3 kJ per kilogram. So, makalculate natin ang work net natin, and that is 623 kJ per kilogram. Okay, next is the net work output. Ang work output natin is the difference between the heat provided and the net work. So we have 1092.3 kJ per kilogram. Okay, so dito na illustration, it is about the principle of the Carnot cycle. Merong isang inventor, sabi niya, na meron siyang engine na makapag-generate ng 10 kilowatt out of 15 kilowatt na input. At ang temperature ng reservoir niya ay 27 and 427 degrees Celsius. Okay, ang tanong dito is, valid ba ang kanyang claim? Okay, una-una pag titingnan natin, ang output niya is 10 kilowatt. Ang input is 15 kilowatt. Di natin yan masasabi na nag-violate ito ng first law. Dahil ang output natin hindi naman lumampas sa 15 kilowatt. Magiging invalid ito kapag sabihin natin ang output na work is 20, samantala ang input nito is 15 kilojoule. That is the violation of first law. Pero, pag titingnan natin, meron pa isang pwede nating basihan, ang second law of thermodynamics. Na ang sabi doon, na ang efficiency ng isang engine ay hindi na pwedeng lalampas sa efficiency ng engine na working in Carnot cycle at that temperature limit. Okay, kapag mayroong engine at i-compute natin ang pinakamataas na efficiency nito na pwedeng abutin, gagamitan natin yan ng Carnot cycle. At ito ang kanyang efficiency. Meron tayong lower temperature and higher temperatures. So, makompute natin ang maximum efficiency ng any engine, which is in here, 57.13%. Pero, ang sabi ng inventor na ito, sabi niya, ang work output niya is 10, ang work input niya is 15. Meaning, it's equivalent to claiming na ang efficiency ng kanyang engine is 66.67%, which is higher than the Carnot efficiency nandito sa kabila. Ibig sabihin, hindi totoo ang kanyang claim. It is a violation of the second law. So, our answer is, the claim is not valid. Okay, so ngayon pag-usapan naman natin ang Rankine cycle. I-modify lang natin ang ating Carnot cycle kanina, working on steam. Ngayon, meron pa rin tayong boiler. It is regulated to a maximum pressure P2. Meron tayo dyang liquid, and then ininit natin yan. Tumaas ang temperature hanggang naging saturated liquid, hanggang nag-vaporize, hanggang nagiging superheated vapor. Nang ito ay nagiging superheated vapor, in-expand natin ito sa turbine na siyang dahilan ng pag-ikot ng turbine at gumawa ng work, WT. And then, ang mga vapor nito ay inilagay natin sa condenser kung saan atin ito kinondense. Unlike sa Carnot cycle kanina na discuss natin, sa Rankine cycle, ang lahat ng mga vapor ay kailangan itong i-condense. So before natin ito i-pump doon sa ating boiler, make sure na ang ipinapump natin doon is pure condensate, walang halong vapor. Ipapump natin doon at aakyat ang ating tubig doon sa boiler, and then umpisahan naman natin ulit ito ng pag-init. So that's a cycle for the Rankine. Okay. Sa TS diagram, ito ang hitsura ng ating Rankine cycle. Meron tayong dalawang pressure limit, pressure P2 at pressure P1. Ang pressure P2 is the pressure in the boiler and pressure P1 is at the condenser. Kung ang state 1 natin is the state before entering the pump, sa TS diagram, this is the condensate at pressure P1. From pressure P1 or from point 1, ipapump natin ito at higher pressure. If the process is isentropic, ibig sabihin vertical ang ating proseso, ay vertical ang line from 1 to 2. After exiting the pump, ang state ng ating water is at state 2. That is the vertical line intersecting the line P2. And then from point 2 to point 3, the water is heated in the boiler. Una, tataas ang pressure, ang temperature to saturation temperature P2, and then mag-vaporize hanggang maging saturated vapor, and then magiging superheated vapor. And then, nang nagiging superheated vapor ito, in-expand natin ito sa turbine, nag-generate ito ng work. And then, ang point 4 natin, pwedeng may mixture ito ng vapor at liquid or purely superheated vapor. And then, from point 4, i-condense natin ang ating mixture into pure saturated liquid. Or, kung mas maaari, dapat subcooled liquid before natin ito i-pump sa boiler. Okay. So, i-determine natin ang mga values na kailangan natin dito i-compute. Unang-una, ano ang output ng plant. But before that, i-compute muna natin ang ibang mga work done kagaya ng work ng pump. Ang work ng pump natin ay mass times VDP. Okay, that is the work by the pump. Or pwede nating i-rewrite ito as since mass times specific volume is total volume, so we have capital V, and dP is the difference in the pressure, high pressure and low pressure, that's P2 minus P1. And the heat added is the change in enthalpy from 0.3 and 2. So H3 minus H2 times the mass of the water. Okay, ano ang value ng H2 natin? Unlike H1, ang H1 natin makita agad natin yan sa steam table at the saturated liquid value. At point 2, pwede natin makompute yan gamit din ang enthalpy at point 1. That is enthalpy at point 1 or the energy at point 1 plus the energy provided to the water by the pump, which is VDP. Ang specific volume natin is the specific volume at point 1. And then the heat rejected. The rejection process takes place on 0.4 to 1. So we have H4 minus H1 times M. And the work of the turbine takes place on state 3 up to state 4. We have H3 minus H4 times the mass flow rate of the water. Then we'll have the work net to be work of the turbine less the work by the pump. And the efficiency can be calculated by work net over Q added. Okay, isang importante na bagay dito ay ang work ng pump, kung gaano ito kalaki kumpara sa work ng turbine. Baka ang work ng pump sing laki lang ng work ng turbine. So wala na tayong network. The ratio of the work of the pump to the work of the turbine is called the back work ratio. Okay, ito ang ating TS diagram para sa problem na ito. Working pressure of 8 megapascals and 0.008 megapascals. Pero, according to the problem, the steam exits the boiler at saturated vapor state. So, i-modify natin ang ating TS diagram. So, ang point 3 natin is saturated vapor. Okay. So, i-determine natin ang back work ratio. So, back work ratio natin is work of the pump divided by the work of the turbine. So, work of the turbine is M times change in the enthalpy between 3 and 4. Ang H3 natin is a saturated vapor state. So, titingnan natin kung ano ang kanyang enthalpy. Sakaling walang dalang, kapag ang exam natin ay walang walang dalang steam table, dapat ang mga value na ito ay naibigay. Pero kapag hindi naibigay, ibig sabihin dapat merong naka-attach yan na steam table. Okay, titingnan natin ang value ng H3 mula doon sa ating steam table. Buksan natin ang ating steam table at titingnan natin ang value ng point 3. Ang point 3 natin ay saturated. So, pupunta tayo doon sa part ng steam table kung saan merong column ng pressure at temperature na magkatabi. Kapag merong ganon, ibig sabihin, ang table na iyan is for saturated properties. And then, i-identify natin ang pressure or temperature. In this case, pressure na 8 megapascals or 8,000 kilopascals. Okay, ang gusto natin kukunin dito ay ang enthalpy at point 3, which is Hg. This one, this column. Okay, ang value natin ng H3 natin is 2,707.55. Okay, maliban dito, i-identify din natin ang isang property dito which is kakailangan natin in the future calculation. 5.7458 entropy natin yan. That is Sg, entropy of the saturated vapor. This correspond to this vertical line sapagkat ang point 3 at point 4 ay magkaparehas na entropy. So that line is 5.7458 na entropy. Okay, so ang next natin i-identify ay ang H4. Ang H4 natin ay nasa lower pressure na. So binuksan natin ang ating steam table at lower pressure at hinanap natin doon ang 8 kilopascals. Pag titingnan natin ang 0.4 natin, ang Hg natin dito is 2577.34. But this is not our 0.4. This is the enthalpy of the saturated vapor at that pressure. Okay, on the other side, meron tayong HF. Enthalpy yan ng saturated liquid at that pressure. Okay, pero pag titingnan natin, meron din tayo ditong HFG. Merong ibang mga steam table na walang FG na property. Ang FG is the difference between the G and the F. Sometimes, pinoprovide ito para hindi na tayo mahirapan sa pag-compute. Ang HFG is the difference between Hg and HF. So, kapag titingnan natin, ang HFG natin is that segment mula sa point 1 hanggang sa point red. So, ang point 4 natin, ang enthalpy, kapag i-compute natin ang enthalpy natin dyan, it must be the enthalpy at point 1, which is 173.8, plus the fraction of 2403.58. That fraction is called the quality. So, depende sa quality ng ating mixture, we can determine the enthalpy at point 4. So, the enthalpy at point 4 is 1.73 plus a fraction of the total length. Isulat natin dito. That is our H4. Okay, pero ano ang X? Ano ang quality? Ma-determine natin yan gamit ang entropy. Dito na ang gamit ng entropy natin. Alam natin na at point 4, ang entropy dyan ay equal sa entropy sa point 3, which is 5.7458. Okay, which is also equal to the entropy at point 4, which can be expressed as the sum of entropy at point 1 and a fraction of entropy from 1 to 4. Okay, yan na yun. Meron tayong SF, kung saan ang SF natin ay ang 0.5924. At ang S sub FG natin ay 7.6372 at 8 kilopascals. So dahil given ang SF and SFG and only X is the variable, then we can determine our X. 0.675. So our X is now solved. So we can now determine our H4. Our H4 is 1796.2. Okay, so let's now proceed to the work of the pump. The work of the pump, mass of the water times the VDP, where V is the specific volume at point 1. At point 1, the pressure is 8 kilopascal, and the VDP, meaning the change in pressure in the inlet and the outlet of the pump, is the two pressures, 8,000 and 8 kilopascals. And the specific volume, punta tayo doon sa ating steam table at 8 kilopascal, titingnan natin ang VF. That is the specific volume of the saturated liquid. We have that value. And then, kompleto na ang ating mga variables. So, eliminate M and then we can compute that the backwork ratio is equal to 0.008. Okay, so determine the thermal efficiency if the pump and turbine have isentropic efficiency of 85%. This is our TS diagram. Again, this is the same problem as earlier. Pero ngayon, ang ating pump and ang ating turbine ay hindi 100% efficient. So, una, identify natin that the temperature difference is 8,000 minus 8. So that is our DP. And we have already identified our point 1 with specific volume of 0.001008 and enthalpy of 173.8 from the previous problem. And we have already identified point 2, which is equal to H2. Okay, to identify point 2, we have H2 is enthalpy at point 1 plus specific volume at point 1 dP. Meron tayong H1, meron tayong specific volume, at meron pang tayong dP, meaning makalculate natin ng ating H2. Now, at point 3, we have already identified that from the earlier problem. And the point 4 also, na-identify din natin yan. Okay, so it's now complete. We are now ready to compute the thermal efficiency. Thermal efficiency is the work net over Q added. Okay, ang work net natin is already given. It's 100,000 kilowatt. Pero ang MQA natin hindi given, but we know it is equal to the mass flow rate times the change in enthalpy in point 3 and point 2. Point 3 is defined. Point 2 is already defined, meaning we have H3, we have already H2. The only unknown here is QA and M. So we'll determine M. Ang isang paraan na pwede natin ma-determine ang M is the fact that we know that the net output or the net work output is 100,000 kilowatt. And the net output or the net energy output is dependent also on the mass flow rate. Kasi kapag dinoble natin ang mass flow rate, madodoble din yan. Meaning, we can write the work net as work of the turbine less the work of the pump, where the work of the turbine is equal to this formula. So, kapag compute natin, the work of the turbine is equal to the change in enthalpy between 0.3 and 0.4 if the turbine is 100% efficient. But since the turbine is not 100% efficient, it is 85% efficient ang kanyang isentropic efficiency. Ibig sabihin, only 85% of this energy will be converted into the work of the turbine. And the work of the pump. The ideal work of the pump is equal to this formula. Specific volume at 0.1 times dP. Okay. Pero, dahil ang pump natin is not 100% efficient, meaning only 85% of the work of the pump is converted into the energy of the water. Okay, papansinin po natin ng efficiency natin dito ay hindi magkaparehas ang posisyon. Sa turbine, inilagay natin ito sa kabila. Sa pump naman, dito naman sa kabilang side. Sapagkat ang pump dito ang source ng energy. Ang source ng energy natin is ang pump. Nag-supply ng energy ang pump, pero hindi lahat ng energy niya ay ginamit upang itulak ang tubig. It's only 85% of that energy, meaning 85% of the pump. Samantala sa turbine na naman, the source of the energy is the expanding steam. Kapag 100% efficient ang turbine, ibig sabihin lahat ng energy ng steam i-absorb nun. Pero sapagkat hindi siya 100% efficient, meaning 85% ng energy ng steam ang kanyang na-absorb. Okay, so finally, ang ating work ng pump is equal to this formula. Then we can rewrite now the work net to be equal to this equation. Work net 100,000. Work of the turbine is that expression times 0.85, and work of the pump is that expression divide 0.85. Given po lahat yan, merong H3, meron ng H4, meron ng specific volume 1, at meron din tayong dP. The only variable here is M. And M is equal to 121.64 kilograms per second. And substituting everything to the original equation, makompute natin ang QA, at substitute natin doon sa taas, makompute natin ang ating efficiency. Okay, ito ang ating TS diagram. Meron tayong dalawang working pressure. Meron tayong pressure at the condenser side and the pressure at the boiler side. Pero meron tayong staging dito nangyari. Meron tayong isa pang is pressure which we will identify 0.7 megapascals. Okay. Unang-una at state 1, ang tubig natin is saturated liquid. We pump it to the pressure of the boiler at 8 megapascals. Pagdating sa 8 megapascal, ininit natin ito hanggang naging saturated liquid, hanggang naging saturated vapor, hanggang nag-superheat. The point 3 is a superheated state. From point 3 na naman, atin itong in-expand sa turbine, first stage of the turbine, and then that is point 4. And then from point 4 naman, atin itong ininit muli, reheat, that is 0.5 at a lower temperature than state 3. Then from 0.5 again, it is expanded to the final stage of the turbine, and then exits, the water exits at 0.6. From 0.6 again, recycle natin ang tubig. we condense it, and then we pump it to the boiler again. Okay, the pressure, the working pressure of the pump is 8,008 kilopascals. So the change in pressure is that difference. We have already identified specific volume 1 and H1 from the previous problems. We have already values for point 2 and for point 3. Titingnan pa natin yan sa steam table. At point 3, ang temperature natin dyan is 480 and it is superheated. Ang temperature 480, pressure is 8 megapascals. Bubuksan natin ang ating steam table, particularly the superheated region. Okay, doon tayo sa table kung saan meron naka-label sa itaas na pressure. And then titingnan natin ang temperature na 480 para malaman natin ang enthalpy dyan. Okay, meron tayong 450, meron tayong 500. Walang 480. Meaning, ang enthalpy natin dyan must be between these two values also. So, makompute natin ang H3 natin, which is 3,148.48 by interpolation. Hindi ko na i-detalye dito ang interpolation. Pakibalikan na lang ang video natin sa thermodynamics para sa interpolation. Doon i-detalye natin ang computation. Okay, isa pang value ng kukunin natin sa point 3, which is important for our later calculation, is the entropy. Here, using interpolation again, we have our entropy at that point is 6.6577. Okay, next, it is expanded to point 4. Bubuksan ulit natin ang ating steam table. Pero titingnan muna natin ang superheated region ng 0.7 megapascals. Titignan natin dyan ang entropy. The entropy there, the lowest entropy there is 6.7. Compare that to entropy at 0.3. The entropy at 0.3 is 6.6. It is smaller than the entropy of the saturated vapor at 0.7 megapascal. Okay, sapagkat ang entropy sa point 3 papunta sa point 4 ay dapat magkaparehas. Since ang entropy dito na binigay sa superheated is mas mataas, ibig sabihin ang ating point 4 must be saturated. Okay, bubuksan natin ang ating saturated region kung saan titingnan natin ang 700 Pascal at titingnan natin ang enthalpy. So ito ang enthalpy ng liquid natin. Ito ang enthalpy ng ito ang HFG natin. Given the HF and HFG, we can determine the value of H4, which is HF plus X times HFG. Pero ano ang X natin? Ang X natin, makompute natin yan given the fact that entropy at point 3 and entropy at point 4 are equal. Meaning, 6.6577 is equal to entropy of the saturated liquid at point 4 plus the SFG at point 4 and the HFG in that pressure times the quality. Okay. The SF and SFG are here sa ating steam table. Substitute that to that equation, makompute natin ang ating quality. Then substitute natin dyan sa original, then we can have H4 value. Okay, next proceed tayo sa point 5. Point 5 again is a superheated vapor. So pupunta muli tayo sa superheated region at a temperature of 440. That is somewhere here. Again, by interpolation, makompute natin ang H5 natin dyan to be equal to that value. And don't forget, kukunin din natin ang entropy dyan sapagkat equal din yan sa entropy sa 0.6. And then let's now go to 0.6. Sa 0.6 naman natin, ito yon 8 kilopascal. Ang HF natin dyan, 173. At ang distance natin na HFG is 2,403. Okay? At ang entropy natin dyan, 7.7537, is also equal to SF plus X SFG at that pressure. Substitute natin lang lahat, makompute natin ang ating X, and that is the value. Okay? And makompute natin ang ating H6. Now, nakompute na natin ang lahat ng mga enthalpy of all the points provided. Makompute na natin kung ano ang work net natin. Work net is work done by the first turbine plus the work done by the second turbine less the work done by the pump. The work net is 100,000. The work done by the first turbine is equal to that value. Of the second turbine is equal to that value. And work done by the pump is equal to that value. Since all of that value are given except for the mass can be determined 65.66 kg per second. Or in per hour basis, that is 236,376 kg per hour. Okay, so nandito ang ating turbine. The water enters at point 1 with an enthalpy of 3,374. And then we have the bleeding at point 2 with an enthalpy of 2,797. And the water exits the turbine at point 3 with an enthalpy of 2,346. The problem is asking for the mass flow rate of the steam. Since the mass flow rate of the steam is dependent, the output power of the turbine is dependent on the mass flow rate of the turbine. Then, meaning we can use the formula for the work output of the turbine. Assuming that the mass flow rate at point 1 is m, then the mass extracted at point 2 is 0.172 of m. Then, we can calculate the work of the turbine as the energy released or absorbed by the turbine from point 1 up to point 2. And that is equal to that formula. The difference in the enthalpy from point 1 and point 2 and the mass flow rate during the expansion of the mass m from point 1 to point 2. Aside from that, the water also or the turbine also absorbs energy from the expanding steam from point 2 to point 3 with an enthalpy change of H2 minus H1. At that point, the mass flow rate is now 0.828 of m, which is a net of 0.172. Okay, so we have the work net of the turbine and we have also the value of the enthalpies. So our only unknown here is m. So makompute natin ang m natin and that is equal to 126 kg per second. Okay, so pupunta naman tayo sa geothermal power plant. Ang geothermal power plant ay power plant ito na kina-convert ang geothermal energy into electricity or any usable energy. Kanina sa ating steam power plant, meron tayong boiler, meron tayong turbine, meron tayong condenser, at meron tayong pump. Sa geothermal power plant, dinidrill natin ang crust hanggang maabot natin ang certain depth like say 4 kilometers up to 6 kilometers. At that depth, medyo mataas na ang temperature doon sapagkat malapit na ito sa mantle kung saan nandun ang molten material na masyadong mainit kagaya ng lava or magma. Sa ilalim ng lupain natin ay meron ding mga tubig doon na, naka-stuck, no? Due to ah, ilang taong pag-uulan na ipon doon sa ilalim. At kapag i-drill natin yon, at dahil sa mataas na temperature doon at mataas na pressure ay itutulak ito pitaas. So kapag dinrill natin ang ating crust at that depth, akit ang ating high pressurized water with high temperature at i-expand natin ito sa ating tinatawag na flash separator. Pag-expand ito sa flash separator, magkakaroon ito ng magsiseparate ang liquid and vapor. So, ang pressure nito ay mataas. Ang vapor natin ay siyang gagamitin natin para doon sa pagpagana ng ating turbine. And then, i-condense natin ang ating vapor at i-inject natin ito pabalik sa ating earth. Samantala, ang condensate naman sa ating flash separator ay ating itong inject pabalik sa earth. Okay, so, ang geothermal power plant ay may mas simpler na schematic diagram kumpara sa ating steam power plant. Pag titingnan natin ang ating TS diagram, ito ang state ng tubig bago ito na flash doon sa ating flash separator. Ito naman ang state ng tubig nang nag-expand ito sa ating turbine. Ang state ng tubig na yan ay saturated vapor. At ang state 3 naman is yung lumabas na sa turbine. Sa TS diagram, ito ang kanyang itsura. Point 1 is the state of the water. Ang state na ito is actually a compressed liquid, but its property is close to the property of a saturated liquid, kaya nilagay lamang natin ito as a saturated liquid. That is a high pressure state. And then, ipinasok natin ito sa flash separator at a lower pressure, but a lower pressure, but still enough to generate power on the turbine. And then, i-flash natin yan. When we flash it, ibig sabihin ang ating enthalpy is the same. Kung ano ang enthalpy sa point 1, ang final enthalpy nito after flashing is still the same. Okay, then that is our point 2. Our point 2 is the saturated vapor. Yan ang kakailangan natin. Ito ang kailangan natin upang patakbuhin ang ating turbine. And then the water exits the turbine at point 3. And then atin ito i-condense and then inject back sa earth. Okay. Ang work ng ating turbine is the change in energy from point 2 to point 3. Where the enthalpy at point 2 is the enthalpy of the saturated vapor at that pressure. And the mass flow rate of M2 is the fraction of M1. Sapagkat hindi naman lahat na vapor or hindi naman lahat ng tubig na drill natin ay nagiging vapor. Iba nito ay nagiging condensate. So, ang gagawin natin dyan ay i-determine natin kung ano ang X, which is the quality. X is the amount of vapor. So, it's a fraction of M1. Okay, so ito ang ating TS diagram para sa ating geothermal plant. I-determine natin ang work ng ating turbine. Okay, may net work ang turbine, which is 80 megawatt. Ang tanong ng problem is, what is the change in enthalpy from point 2 to point 3? Okay, so alam natin na ang ating work net is 80,000 kilowatt and equal to M2 times the change of enthalpy between 2 and 3. But what is M2? M2 is a fraction of M1. A fraction is called the quality. So, i-determine natin muna kung ano ang quality. We can use that by comparing the enthalpy of point 1 and at point 2. Pero sinabi sa atin ang quality. The quality is 20%. So meaning 20% of 400 is the mass of the vapor. So the mass of the vapor is 80. So we can determine the change in enthalpy to be equal to 1000 kilojoule per kilogram. Okay, so now dito na problem ibinigay ibinigay ang mga properties at different points. Mas maganda kapag ganito ang nagiging ah, problem. Meron ng given. Mahirap nga lang kapag wala ito kasi titingnan natin ito sa steam table. Okay, ito ang TS diagram natin. Unang-una, ang state 1 natin is at 204 degrees Celsius. May enthalpy dyan, which is 870.51. Next, it is expanded to the flash separator at a pressure of 1.04 megapascal. Ang enthalpy dyan is equal sa enthalpy 1 dapat. Okay. Dahil during flushing, wala namang energy na tinatanggal. Ibig sabihin, ang energy at point 1 is the same as energy at point S, that red dot. And then here, ang vapor ang importante para sa atin dahil itong gamitin natin para sa pag-expand. Para ma-determine natin ang ating mass flow rate, M2, ay kailangan muna natin i-determine ang ating quality at point S. Para ma-determine natin ang quality natin dyan, alam natin ang enthalpy dyan is also 870.51 equal to enthalpy at point 1. But we can express that enthalpy also as the sum of the enthalpy of the liquid and the enthalpy of the vapor. Since the vapor is X% of the total liquid, so we have this equation. Enthalpy of the liquid 770 and the HFG is 2009.2. So makalculate natin ang X natin is equal to that value. So that's the quality of the water at 1.04 megapascals. So ang amount ng vapor nandyan is 0.0498. At point 2, ang ating mass flow rate dyan is 0.498 of M1. And ang enthalpy natin dyan, titingnan natin yan, nandyan sa taas, at 1.04 megapascals, Hg is 2779.6. Where the entropy is Hg pa rin, 6.5729. Gamitin natin yan para malaman natin ang state 3. At state 3, ang pressure is 0.034 megapascals. What is the enthalpy at point 3? Okay, i-determine pa natin yan. Pero ang alam natin, na pwede natin ito i-compute gamit ang formula na HF plus X times HFG at that pressure. At 0.034 megapascals, ang HF 301, ang HFG 2328. And the unknown is X. But we can determine the value of X here. Dahil, alam natin ang entropy at point 2 is also equal to the entropy at point 3, which is 6.5729, which can be written also as the sum of the entropy of the liquid and the HFG at that pressure, which is 0.9793 plus X times 6.7463, where we can determine X and then substitute that to the enthalpy formula sa H3, then H3 will be 2232.29. Okay, kompleto na. Then we can now determine the mass flow by using the energy or the work net from 2 to 3. Ang work done ng ating turbine is the energy change from point 2 to point 3. Okay. But the turbine has an efficiency of 75%. This energy is the maximum ideal if the turbine is 100% efficient. Since the turbine is not 100% efficient, it means that the energy that is absorbed by the turbine is only 75% of that available energy from the steam. And that is the work done by the turbine, which is equal to 50,000. Since M2 is equal to 0.0498 M1, and our H2 and H3 are also given, then we can determine M1 to be equal to 2,444 kilogram per second.